Flip a switch and a room fills with light so fast your brain registers it as instant. But inside that glass bulb, something absolutely bonkers is happening. A piece of metal is literally tearing itself apart atom by atom just to give you light. And the crazy part is we designed it to do exactly that. Let me explain what is happening inside that bulb right now. The key component is a tiny coil of wire thinner than a human hair. It is called the filament, and it is made of tungsten. Tungsten is a metal so tough that it does not melt until the temperature reaches 6,200 degrees Fahrenheit. That is hotter than the surface of the sun. When you flip that switch, electricity rushes through the copper wires in your wall and into the bulb. The electrons slam into the tungsten filament at nearly the speed of light. The filament resists the flow of electrons, and that resistance creates heat. Within a fraction of a second, the filament heats up to 4,500 degrees. It glows white-hot like a miniature star trapped inside a glass bubble. This is called incandescence, the same process that makes campfire embers glow orange and makes the sun radiate light across 93 million miles of space. But here is the problem. If the tungsten filament were exposed to air at 4,500 degrees, it would instantly burst into flames. Tungsten plus oxygen at that temperature equals a tiny explosion. So the bulb is filled with argon gas, an inert gas that refuses to react with anything. Argon is one of the noble gases, which means its atoms have a full outer shell of electrons. They are chemically satisfied and will not bond with tungsten, no matter how hot you make them. The argon also has a second job. It slows down the evaporation of the tungsten atoms, because at 4,500 degrees tungsten does not just glow, it sublimates. That means it turns directly from solid metal into a gas, skipping the liquid phase entirely. Atom by atom, the filament is evaporating into the argon gas while you read this sentence. Over hundreds of hours, the filament gets thinner and thinner and thinner. Eventually, one section becomes so thin that it cannot carry the electrical current anymore. The filament snaps. The light goes out. And you say the bulb burned out. But technically, it did not burn. It evaporated. If you look closely at a burned-out incandescent bulb, you can sometimes see a dark smudge on the inside of the glass. That smudge is made of condensed tungsten atoms that evaporated off the filament and stuck to the glass. You are literally looking at the ghost of the filament that used to be there. Now, modern LED bulbs work on a completely different principle, and they are about 10 times more efficient. LED stands for light-emitting diode. Inside an LED bulb, there is no filament and no argon and no burning and no sublimation. Instead, there is a tiny chip made of semiconductor material, usually gallium nitride. When electricity flows through this chip, it forces electrons to jump from a higher energy level to a lower one. Each time an electron makes that jump, it releases the extra energy as a particle of light called a photon. This is called electroluminescence, and it is fundamentally different from incandescence. An incandescent bulb makes light as a byproduct of extreme heat, which is why 90% of the electricity goes to heat, not light. An LED makes light directly without needing to get hot first, which is why it uses 90% less electricity and lasts 25 times longer. But there is a catch. A single LED chip only produces one color of light, and that color is blue. Every white LED bulb you have ever seen is secretly blue. Engineers coat the blue LED chip with a thin layer of yellow phosphor. The blue light from the chip hits the phosphor, and the phosphor absorbs some of the blue energy and re-emits it as yellow light. The blue that is not absorbed mixes with the new yellow, and your eye perceives the combination as white. You can actually see this if you look at an LED bulb through a diffraction grating or even a CD held at an angle. The spectrum will show a massive spike in the blue region and a broad hump in the yellow region. It is not natural sunlight, which contains every color smoothly blended from violet to red, which is why LED light can sometimes feel cold or harsh compared to the warm glow of an old-fashioned bulb. Engineers adjust the thickness and composition of the phosphor coating to shift the color balance. A warm white LED has a thicker phosphor layer that absorbs more blue and produces more yellow and red. A cool white LED has a thinner phosphor layer so more blue leaks through. The entire LED revolution was enabled by 3 Japanese scientists who figured out how to make a practical blue LED in the 1990s. Before their breakthrough, red and green LEDs existed for decades, but nobody could make a bright blue one. And without blue, you cannot make white. They won the Nobel Prize in 2014, and the ceremony was lit almost entirely with their own blue LEDs converted to white. So the next time you walk into a room and flip a switch, remember what you just did. You sent electrons screaming through a copper wire at nearly the speed of light. You heated a tungsten filament to half the temperature of the sun while an invisible cloud of argon gas protected it from exploding. Or depending on your bulb, you forced electrons in a gallium nitride crystal to jump off an energy cliff and release blue photons that then crashed into a yellow powder and combined into white light, all in less time than it took you to read this sentence. Light bulbs are honestly ridiculous, and now you know exactly why. If that lit up something in your brain, hit like and subscribe and ring the bell, and drop a comment telling me what everyday invention you want explained next. I have got a list going, and the most requested one becomes the next video.